Hey class, Mrs. Anderson here. This video is going to be on graphing quadratic equations in Vertex and Intercept form. So we've been working with quadratic equations like y equals ax squared plus bx plus c. This is in standard form, and today we're going to look at Vertex and Intercept form of that. So here is the vocabulary review. The shape when you graph a quadratic equation it makes is called a parabola. It makes this kind of like U shape, and it can either open up or it can open down, which we'll see. And then the line that divides the center, so it's like symmetric across this vertical line, that's called the axis of symmetry. The maximum or minimum point here is called the vertex. And then you have the y-intercept where it intersects the y-axis. And then we actually have four names for when it intercepts the x-axis. We could call those solutions, roots, zeros, or x-intercepts. So four names for those points. So our parent function of our quadratic equation is y equals x squared. So y equals x squared has a vertex at 0, 0, because when you plug in 0, 0 squared is 0. And then the parabola follows this pattern. You think of it as x and y. So 1 squared is 1, 2 squared is 4, 3 squared is 9. So it follows this pattern from the vertex over 1 up 1, from the vertex over 2 up 4, and then from the vertex again over 3 up 9. So this gives us half of the parabola. To make the other half, you would reflect it over the axis of symmetry, which would be the y-axis here, since our vertex is at the origin. So we could go over 1 to the left and then reflect this second point over, so right there, and then reflect that point over, so 3 away on the right, 3 away on the left at 9. And then that can make our parabola. So we call this the parent function. So it has no shift. It has started at 0, 0. There is no vertical shrink, no vertical stretch. This is the standard width, and it hasn't been shifted. So this is the pattern we're going to use to graph the rest of the parabolas, basically. So what happens when a is not equal to 1? Well, let's plug in 0, 1, 2, and 3. And then we'll think of just x and y as just y equals x squared. So 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9. And then if our a value is 1/2, then we would take our x squared value times 1/2. So you would take 1/2 times that, whatever you got for y in the middle column. So 0 times 1/2 is 0 still. 1 times 1/2 is 1/2. 4 times 1/2 is 2. 9 times 1/2 is 9/2, or 4.5. So you can see by the very first one, 0, 0 stays the same if you look at just the first and last column now. And maybe I won't cross that out yet. So the change in the a value doesn't shift the parabola at all. It would still start at the vertex of 0, 0. But instead of going over 1 up 1, you would go over 1 up 1/2. And then instead of going over 2 up 4, you would go over 2 up 2. And then over 3 up 9. And now it's over 3 up 4.5. So this is going to essentially make the parabola rise slower, which will in turn make it look wider. And then we call this a vertical shrink or vertical compression in some books. So we call this a vertical shrink. So it's going to be wider, the a value, but it doesn't move, the shift doesn't move. Okay, so if you think about just the y equals x squared first, so y equals x squared, and I choose the same points, 0, 1, 2, and 3. 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9. Then if a is 4, then it's 4 times those y values that we got in the middle here. So 0 times 4 is still 0. 1 times 4 would be 4. 4 times 4 would be 16. 9 times 4 would be 36. It's blanked out there. Then we would graph those values instead of our middle ones. So notice our vertex would still be at 0, 0, so it doesn't change the shift. It doesn't move the parabola. But instead of going over 1, up 1, now we're going over 1, up 4. And then we're going over 2, up 16 instead of up 4. So this one is going to make the parabola, it's going to rise a lot faster. And that's going to make it more narrow of a parabola. This one's going to be wider. This one's going to be more narrow because it's rising so much faster. So this is when we have a vertical stretch. It's being pulled up vertically a lot faster. Okay, and what happens if a is -3? So if I have the same values for the parent function, just y equals x squared, so 0, 1, 2, 3, 0, 1, 4, 9, and then this time a is -3, so -3 times the middle column. The vertex will stay at 0, 0 because 0 times -3 is still 0. Then 1 times -3 is -3. 4 times -3 is -12. 9 times -3 is -18. And then you would graph the first and last column because it is -3x squared. And so here I'm going over, so over 1. Typically I went over 1, up 1. This one is over 1, and then these are all going down, down 3, over 2, down 12. And it's going down a lot faster. So not only is this a value making the parabola open downward, it is also a vertical stretch again because it is falling in this case, but faster than just going by the typical a value of 1. So it'd be a lot more steep, and it would make the parabola more narrow, plus it would open down instead of up. So that's what the a value is responsible for. So vocab review. I call this a review because technically you did learn this in Algebra 1. How much of it you remember is another story. So vertex form is y equals a times the quantity of x minus h squared plus k. A is responsible for being wide, making the parabola more wide or more narrow, kind of like we just talked about. It also affects if the parabola opens up or down. So in technical terms, it's whether or not it's a reflection over the x-axis, or if it opens, or if it's a vertical stretch or vertical shift. Vertical stretch or vertical shrink, sorry. H is our x coordinate from our vertex. So our vertex is the hk values. So h is the horizontal shift because h is going to move it right and left. And k is the y coordinate of the vertex, so it's going to move it up and down. So that's our vertical shift. Here's some more information about a. So a tells us, you know, what I just said, but written out a little bit more. Okay, notice in the equation that it's x minus h and then plus k. So if we're looking for our vertex in our first example, y equals 2 times the quantity of x plus 3 squared minus 4, we're going to get our vertex from these two values right here. Our vertex for our h coordinate will come out as -3, and our k value will be -4. So in our general equation, it is a x minus h squared plus k. So in order for this to be a +3 there, it would have had to have been plugged in as a -3, because x minus -3 squared plus -4. So now you can see that like two negatives would have made that a plus there, and then -4 at the end is the same thing as -4. So what you need to remember is that the h coordinate will always come out opposite of what is in the parentheses. The k coordinate will be the same. So our vertex will be -3, 4. Then the a value is the leading coefficient, so the a value is 2. So we're going to graph -3, 4 is our vertex, so that's left 3, then down 4. And then I'm going to make my axis of symmetry right here as well. So we can say axis of symmetry. Let's just call that AOS for now. Is going to be the line x equals -3. Then I can graph my parabola by choosing some points, and I'm going to graph the parabola using the parent function idea. So I'm going to graph the y equals x squared essentially. So I'm going to do the 0, 1, 2, and 3. 0, 1, 4, 9. So the squares of the first one. And then my a value in this case was 2. So 0 times 2 is 0. 1 times 2 is 2. 2 times 2 is 8. 4 times 2 is 8. 9 times 2 is 18. So I'm graphing the first and middle column because my function has an a value of 2. Remember that the vertex, or the a value, does not move the vertex. You would still start at the origin for the parent function. So for this one, I'm going to start at my vertex, which is -3, -4. So I need to start there. So sometimes I'll draw a dashed line both directions and treat that as my new origin point. So when I graph 0, 0, that's my vertex point. Then I graph, typically I would graph over 1, up 1, but for this parabola, I'm going to graph over 1, up 2. So from the vertex, I'm going to go over 1, up 2, then reflect it over, so 1 away from the other side. Then I'm going to go over 2, up 8. So from the vertex, over 2, up 8. So 2, 4, 6, 8. And then reflect that point over 2 away from the axis of symmetry on the right, so 2 away on the left. Then over 3, up 18. That's going to be off my graph, and I have 5 points, so that should be plenty to graph your parabola. Then I'm going to draw that. Since this opens up, our a value is positive, the vertex is going to be a minimum point. It is the lowest point on the graph. That minimum point is at y equals -4. That's the value of the minimum, because that's the lowest y value. The domain, remember, think back to like quadratics, y equals x squared. There are no restrictions to what you can plug into x squared. You can square any real number. That means our domain are all our x values that are real numbers. So x is an element of the real numbers. Now our range corresponds to our output values. So only the y values that are above, if you look at our graph, we don't have any output values down here. So all our y values are at -4 or above. So our range will be all the y's greater than or equal to -4. And it'll look a little different if it opens down, but you'll get the idea. Okay, graph this one in vertex form. So our vertex is going to be 2, 6. So it's going to be opposite of this one, -2, so 2, and then the same in the end, 6. Our a value is our leading coefficient. We have a negative out front. That means a -1. So graph the point 2, 6. And then you can draw your axis of symmetry. You're going to need that. So axis of symmetry will be x equals 2. So the axis of symmetry always corresponds to the x coordinate of the vertex. Then we're going to make our parent function table, which will be 0, 1, 2, and 3, then 0, 1, 4, and 9. And then a is -1. So -1 times the middle column. So our vertex won't change. Then instead of going up 1 over 1, we're going to go down 1, down 4, down 9. So I took the middle column times -1. And then I'm going to graph those. So when I graph the 0, 0 point, that's my vertex. Then I graph 1, -1. From the vertex, over 1, down 1, reflected over. Then over 2, down 4. Over 2, down 4, and then reflect that over. Then over 3, so over 3 from the vertex, then down 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Then reflect that over. 1, 2, 3, 1, 2, 3. And then you can draw your parabola. So since this one opens down, the vertex is actually a maximum point this time. The maximum point would be that y value. The highest y value here would be 6. So the range is going to correspond to that 6. Since it opens down this time, all our range values are all less than or equal to 6. The domain are all real numbers again. So there are no restrictions to what you can or plug in for x. So all real numbers. Okay, part 2 is graphing in factored form. So remember, factored form is y equals a x minus p times x minus q. Now you might say, well, I don't know if I remember that. But what if I wrote like y equals x minus 3 and x plus 5? And they say, oh, okay, that looks familiar. So factored form or intercept form is what we've been working with when we were solving parabolas and etc. So P and Q are the x-intercepts, and A value still tells us if it opens up or down. And then if it's a vertical shrink or a vertical stretch. Sorry, I was just responding to a student quick. Okay, so here's our first example. So what direction does the parabola open? We're looking for the A value. The A value is negative out front, which means it's a -1, which means it would open down. Then you're going to find the x-intercepts. So the x-intercepts lie along the x-axis, and that is where the y value equals 0. So all of the x-intercepts are like 4, 0. So you need the solutions. So you're going to set each factor equal to 0, so x equals 2, or x plus 4 equals 0, so x equals -4. Those are your x-intercepts, which could be written as x-intercepts like 2, 0 and -4, 0. So if you remember back to the vocabulary, we call x-intercepts, another name for x-intercepts are solutions, because they are the solutions to the equation, or what makes the equation equal 0. So you've been solving, you've been finding x-intercepts. So we can start by graphing those. 2 and then at -4. Then you know that a parabola is symmetric. So to find the axis of symmetry, you need to find halfway between these 2 points. And you might be able to just eyeball it and say, okay, -1 is halfway between -4 and 2. Mathematically, you can add the 2 together, so P plus Q, and then divide it by 2. So x equals, you do 2 plus -4, and then divide it by 2. You'd get -2 divided by 2, which is -1. So, and I've drawn my axis of symmetry there then. Then to find the vertex, you know that the vertex lies along the axis of symmetry line here, so somewhere along this dashed line. So if I plug in -1 for x, because my vertex is going to have an x coordinate of -1, then I can solve for my y coordinate using my original equation. My original equation was y equals -x minus 2 times x plus 4. And maybe we want to put -1 here. So then plugging in -1 for the x. So then y will equal -1 times -1 minus 2 times -1 plus 4. So that'll be -1 times -3 times +3. And then multiplying, this would be 3 times another 3 would be +9. So my vertex would be -1, 9. So then I technically have enough points to graph this parabola because I have the x-intercepts and the vertex. If I wanted a couple more points, I could make my graph a little bit more accurate, use the parent function. So using the pattern of the parent function, so choosing 0, 1, 2, 3, 0, 1, 4, 9, and then a was -1, which means that it would be -1, -4, -9. So then from the vertex, instead of going over 1 up 1, you'd go over 1 down 1. And there I found the y-intercept, so that would be helpful if I needed to know that. And then over 2 down 4, reflect that over, and then over 3 down 9 gets me to my x-intercepts. So there's my parabola. So this would be a maximum point. The domain would be all real numbers still. And then the range would be all of my y values. My maximum point is at y equals 9. So my range would be all my y values that are less than or equal to 9. Perfect. And then it says, compare to the parent function. So if I compare this to the parent function, I had an a value of -1. So if we just think about that, our steepness necessarily didn't change. Instead of going over 1, up 1, it went over 1, down 1. Instead of going over 2, up 4, it went over 2, down 4. But it didn't rise or fall any faster. And so we would say that, you know, it has like the standard or the same width, I guess. However, it opens in the opposite direction because the parent function opens up, opens opposite direction, and then the parent function starts at 0, 0, and this one starts at -1, 9. So this one has been shifted left 1 and up 9. So to the left of 1 and then up 9. So that's the vertex -1, 9. So up, left, and then up. So, okay, let's do one more. I know this is getting a little long, but so this parabola opens up because our a value is a positive, so it opens up. Our x-intercepts are going to be our solutions when our equation equals 0. So x plus 6 equals 0, we're going to get x equals -6. We actually have two x plus 6's, so x plus 6 and x plus 6, our x-intercepts are just going to be -6 and 0 and -6, 0. So, which means that if we find our axis of symmetry, if we only have one point, then our vertex must lie on that point, because if you add -6 plus -6 and divide it by 2, you still get -6. So when the x-intercepts are the same, that implies that it is the vertex point. So if I wanted to plug in, you know, the axis of symmetry, -6, into my equation to get my vertex, I should get 0. So 1/2 -6 plus 6, -6 plus 6, I'm going to get 1/2 times 0 times 0. So -6, 0 is in fact my vertex, which is what happens when the x-intercepts are the same. Which means that we have to use the parent function to find some more points because we don't have the x-intercepts. So the standard pattern is 0, 1, 2, 3, then 0, 1, 4, 9. And then the a value in this one was 1/2. So taking the middle column and timesing it by 1/2. So I did decimals here because they're easier to graph. So the a value doesn't change the vertex. It would stay at 0, 0, which in this problem is -6, 0. And then I would go from my vertex point over 1 up 1/2. So from vertex over 1 up 1/2, and then reflect that over. Then over 2 up 2. And so you can see how this is kind of rising slower. It's going to end up making this graph wider. Over 3 up 4.5. And then reflect that over. So this parabola is going to continue to get wider as it grows to infinity here. And so we would say that this one has a vertical shrink. It has been shifted to the left 6 and up 0. This is a minimum point. The value of that minimum point is 0 because we're looking for the y value for the minimum or maximum. It's a minimum because it opens up. The domain are all the x values that are any real number. You can plug in anything. And then all my y, for my range, all my y values greater than or equal to 0 because they're all above, all my output values here are above that 0 point, that minimum point. All right, if you stuck with me that whole time, good job. Thanks for watching.